Okay. Hello everyone. So let's start with this topic for today's class. That is related to the IC voltage regulators. Okay. So the regulators, that would be like we know that various circuits are available in the form of IC packages. Okay. So let us try to know something about those ICs which are there, which could be used directly for performing these voltage regulation uh, function. Okay. चलो. Okay, then generally we divide we categorize these IC voltage regulators into sectors. One is called monolithic monolithic IC voltage regulators, and the other one is called as the hybrid IC voltage regulator. Okay. And these ICs are very widely used, very popularly used, okay, because we know that the ICs are very compact in size, and they are portable, and they are also very safe to use because uh, all the things are already provided on, all the pins are already provided to you. If we know the functioning of the pin, we can use those pins directly in the circuit. Okay, there is very little to be done with the IC. Just take out the IC and read which pin is performing what function, and just start using that in the circuit. Okay. And generally these IC voltage regulators would be three terminal devices that provide a positive or negative output. Okay. So we have 7800 series and 7900 series. Okay. And 7800 series are for providing positive output voltage. Okay. Regulation, and 7900 series are there for, they are like complement of 7800 series. Okay. So, and they are used for providing negative output voltage regulation. Okay. And both of them would give at least 1 ampere of current. Okay. So they can provide a current of 1 ampere or higher, right? And when you see the internal circuit, internally they contain the reference source, the comparator, amplifier, control, and these are the same blocks of complete regulator circuit that we had seen. Okay. And they also provide the overload protection. Okay. Since in this case, if something happens, then what would IC do? Okay. So there is some sort of protection provided to the IC in case of overload. Okay. Although there is a limit to this also. Okay. You cannot go everything to you cannot take everything to infinite. There is some boundary to that also, but in some sense it is providing some sort of protection also. Okay. Then regarding these monolithic IC voltage regulators. Okay. Monolithic IC voltage regulators, again they come in adjustable form. Okay. Where uh, output is adjustable between two given values. Okay. So it means that output can be adjusted, output can be varied between two given values. Okay. Between two extreme values, one would be the minimum value and the other one would be the maximum value. Okay. Then they come in fixed value IC also, where the output is actually fixed. Okay. And they are smaller in size and provides fixed output voltage. Okay. Then there are some kinds of regulators called as dual tracking regulator, where both positive and negative voltage are available. Okay, since the name dual exhibits something. Dual means it will provide you both a positive and negative voltage at the output side. Okay, and generally these kind of dual tracking regulators would be using a pump inside uh, those circuits. Okay, now in the case of hybrid IC regulators, hybrid means it will combine two or more kind of things. Okay, so it will use IC and discrete components both. Okay, so it becomes hybrid. So IC, we know this thing. Discrete components, we know they are single individual components. So the ICs where there is a provision of there is a combination of both of these two types are called as hybrid ICs. Okay, and or in this case hybrid IC regulators. Okay, and generally they are mounted on ceramic substrate to provide isolation. Okay, and it permits flexibility in the use of circuit components such as regulator chip, transistor chips, resistors and capacitors. Fine, and but they would be a bit larger in size, but provides larger power handling capacity, and this larger power handling capacity comes with the use of these discrete components. Okay, since if we can combine ICs with discrete components, we could certainly increase the power handling capacity of that particular IC. Okay, so this is the basic funda behind these. Okay, now let us see the 7800 series IC. They are fixed, means the output would be fixed, the output cannot be changed. Okay, and one example is from National Semiconductor Company, which manufactures the LM7800 XYZ series. Okay, so LM7800 is common. Okay, and XYZ would vary, where X will denote the subtype. Okay, and YZ would indicate the output value of voltage. Okay, or in some cases you may find simply LM78 and XY. Okay, where XY would indicate the value output value. So coming to this table. Okay, for example, for IC number 7805, the output voltage is around plus 5 voltage. This 05 is indicating its output voltage value. Okay, so output voltage is plus 5, and input voltage required to produce this plus 5 voltage is this much, 7.3 voltage, and this is the minimum voltage. Okay, so minimum voltage that is required at the input side to produce a voltage of plus 5 volts for 7805 is 7.3 voltage. Okay, so take a note of this. And all of these ICs are we had just I have told you that they are having a capacity of handling at least 1 ampere of current. Okay, and they can handle a maximum of 35 or 40 voltage. Okay, so take care of this, that do not increase above this voltage at the input side. Okay, and the dropout voltage typically would be around 2.5 voltage for these cases. Okay, and for example 7806 would give output voltage of plus 6 voltage. Okay, and this will require at least 8.3 voltage at its input side to produce an output of plus 6 voltage. Okay, and again these things are same, this column is also same for these. I see 7808 will indicate its output voltage, so output voltage is plus 8 volts, and it requires at least 10.5 voltage at the input side to produce 8 voltage. Okay, and note down here that if you provide a voltage that is less than this voltage, 10.5 voltage, then in that case you may not be sure that your output voltage will come to this. Your output voltage may be something, but that may not be guaranteed to be around 8 voltage. That may be less than 8 voltage. Okay, at least this much amount of voltage is required at the outputs at the input side to produce a reliable output voltages. Similarly, you can go through these other ICs, let's say 7824, that will provide output voltage of 24 voltage, and at least 27.1 voltage is required at the input side. Okay, and these things are same. So the last column here is talking about dropout voltage. Okay, so look at here, this is V out plus 2.5 voltage. Okay, now the difference between input and output voltage is actually the dropout voltage. For example, in this case, difference input voltage required is 10.5 voltage, minimum input voltage required, and output voltage is 8 voltage, and the difference would be around 2.5 voltage. Okay. Similarly, in this case, again the difference would be 2.5 voltage. In this case, the difference is 2.7 voltage. In this case, the difference is 3 voltage. Okay, so this difference is called as the dropout voltage, and this is generally the minimum voltage. Okay, so dropout voltage is the minimum voltage, that is the minimum difference between the input and output voltage. And this you'll find that this is around 2.5, or in this case 2.3 voltage, and this may vary by some plus minus 1 or 1.5 voltage. Okay, so it indicates that for getting a output voltage of V out value, what should be the minimum voltage applied at the input side. Okay, if we know the value of dropout voltage, we can simply add it to the output voltage to get the input voltage that's required at the input side. Okay, and that particular input voltage will produce a reliable output voltage. Okay, okay, so look at here. Suppose the dropout voltage is the minimum allowable difference between output and input voltages if the output is to be maintained at a correct level. Okay, so suppose for 5 voltage output, minimum input voltage required would be 5 plus 2.5. Okay, it's coming from the table. In the table it was mentioned that the dropout voltage is 2.5 voltage. Okay, so you add that dropout voltage to the output voltage required to get the input voltage. Okay, and this is not an absolute value. Okay, and this may vary by 1 voltage. Okay, it may vary, so it is there to give some indication, some hint that basically look at here. This is the, suppose this is an IC of 7800 series. Okay, it is having 3 terminals: input terminal, output terminal, and the ground terminal. Okay, so this is input, this is output, this is the ground terminal. Okay, so if you are providing a higher input voltage, and if you are getting a lower output voltage, so it means that there is some voltage drop appearing across the IC. Okay, so the voltage drop that appears across the IC, okay, that is particularly the dropout voltage. So the name, as the name suggests, that how much amount of voltage value is there that drops across the IC. Okay, so you get the idea from this from here, right? So as I have told that it is a 3 terminal device, 3 terminal IC. So input terminal, output terminal, and the ground terminal, and you can connect the input and output terminals to the capacitors to make these things more stable, or you may also use these without capacitors, no issues. Okay, but because we know that the capacitors are having the filtering capacity, so we generally use capacitors. Okay, we generally use capacitors. And one of the is also that if there's any rippling that's coming here, any AC part that's coming here in this or in this node, okay, then that may be directly passed to the ground. Okay, so that only it will provide a uh, low resistance part to the AC signals, the AC components. So they might come here and find a low resistance path and may eventually go to the ground. Okay, so it helps in reducing those AC components and that enters into the IC. Okay, and if there is any small AC component that's coming here also, it can also find a low resistance path via this uh, capacitor and can get sink into the ground. Okay, so that the output value also becomes more stable. Okay, so for this purpose generally we can connect capacitors at the input and output terminal. Okay, and similarly the 7900 series are giving an output that's a negative voltage. So 7905 means it will produce a output voltage of -5 voltage. Okay, and the minimum voltage that's required at the input side to produce this much amount of voltage would be -7.3 voltage. Okay. Similarly 7924 will produce an output voltage of 24 voltage, suppose, sorry, -24 voltage. Okay, and the voltage that's required at the input side would be is -27.1 voltage. Okay, okay, now let's see this adjustable voltage regulator. Adjustable voltage regulator. So here the regulator output voltage can be varied over a range, and that is why the name is such, adjustable voltage regulator. Okay, it can be a positive or negative adjustable regulator. Okay, look at this one example. For example is LM317. Okay, let me use this highlighter. Okay, so it's basically a positive adjustable regulator. Okay, and V naught output voltage is in the range of 1.2 to 3.7 volt, 37 voltage. Okay, and can operate between 0 to 125 degrees Celsius. Okay, and the maximum current that it can handle is 1.5 ampere. I think that pen was better. Okay, right. So, and similarly this LM337 is a negative adjustable regulator. So LM317 is a positive adjustable regulator, and LM337 is the complement, we can say, kind of dual or complement of this IC. So actually the complement of LM317, it means that the polarity will be different. Okay, again these are three terminal devices. This is the input terminal, this is the output terminal, and this is the adjusting terminal. Okay, so input voltage is fed here, output is taken across this terminal, and the adjusting terminal is connected to this node. Okay, which is connected between this RH and RL. So basically it's a kind of voltage divider. It's a voltage dividing circuit, simple voltage divider circuit. Okay, and input capacitor is around, let's say, 100 nanofarad. output is 1 microfarad. Okay, now uh, you may think that why is this input capacitor is lower in value as compared to output capacitor. So now try to figure out this, why input capacitor is lower as compared to output capacitance. Just try to think about this. There may be some reason behind this. Okay, now this RH and RL is forming you know voltage divider circuit. Okay, and where there is a provision to vary this RL. Okay, so if we vary this RL value, then accordingly the voltage that appears across this adjusting terminal will also vary. Okay, right, and that will change, that will affect the output terminal voltage here. Okay, because output terminal voltage is the sum of this voltage drop plus this voltage drop. Okay, so if this resistance is changed, that's definitely going to change the output voltage V out. Okay, and these inside these ICs you will find that these are using an op amp. Okay, that is having a relatively high output current capacity. Okay, now this LM78MXY series and LM78LXY series are from a component manufacturing company called as National Semiconductor. Okay, so National Semiconductor manufactures this series LM78MXY and LM78LXY. For example, LM78L62 will give an output voltage of 6.2 voltage. Okay, LM78L82 will provide an output voltage of around 8.2 volts. Okay, then we have many component manufacturing companies. Okay, like Texas Instruments, this ST Microelectronics, National Semiconductors, then Vishay Semiconductors, and many others. Okay, so for example, this ST Microelectronics is again a company that manufacture this IC L78L33ACZ. Okay, so it's a 7800 series, and the output voltage would be indicated by this 33, means output voltage would be around 3.3 voltage. Okay, and different companies have different mechanism for naming their ICs. They follow their different convention for naming the ICs. You will find this. Okay. Basically the series remains same. Okay, so suppose 7800 series is manufactured by National Semiconductor and ST Microelectronics also, but their namings, their individual naming of the ICs that comes from the company may be different. Okay, but again it will contain, the name will contain some information. So for example, here the name contains those values that indicate the output voltage, 6.2, here 8.2, here 3.3. Okay, so this 7800 series have built-in protection against short circuit and overheating. Right. Okay, now let's see a circuit that uses an IC and an extra component, a discrete component, which can be used for boosting the current value. Okay, means it can be used for providing output current value that is more than what is the capacity, that is more than the capacity of the IC itself. So look at this circuit. We have an IC here, input terminal, output and ground, right? the input is connected to this input capacitor, this is output capacitor, and this is simply connected to ground. Okay, and this is the input voltage that's fed in, and this is the output voltage that we are taking out. And the input terminal is basically connected via R1 to V in. Okay, and there is one more resistance R2 that is going into the base of this BJT. Okay, this is an NPN transistor, can be a 2N3772 or TIP2955 or a similar power transistor. So it's basically power transistor, NPN power transistor, and this is the emitter terminal that's coming from here. Okay, and the output or the collector terminal is connected to this output terminal. So, and we know that this collector is the output terminal that will actually give us the output current. Okay, and this terminal is hence connected at the output side of this particular IC. Okay, so this is the branch that is coming out from the IC. So this current here, this would be the summation of this plus this branch current, and the final value of current will increase. Okay, so this is the main idea behind this. Now we know that power transistors are all very good at handling higher amount of current. So if there is some at some application there is a need to increase the amount of current, you can simply use these power transistors at that location. Okay, right, and but take care of the biasing, because this is an NPN transistor. So, and we know that the base emitter junction should be forward biased, and collector base junction should be reverse biased. So while using these two resistors R1 and R2, okay, the value of these two resistors should be chosen such that this base emitter junction remains forward biased, and this collector base junction remains reverse biased. Okay, and that's why the value of R1 should be smaller than R2, so that proper biasing is given to this BJT. And you verify that what happens when R1 is smaller than R2. Does this biasing support this functioning of this BJT? Okay, and what happens if R1 goes above than R2? Then what will be the effect on the biasing of this transistor? Just try to verify this. Okay, and basically I am telling that this R1 is smaller than R2. It means that this value is chosen such that the biasing of this BJT is in proper mode. Okay, so for example, R1 can be 1 hour having 2 watt power handling power dissipation capacity. R2 can be a 10 hour having a power capacity of 1 watt. Okay, C1 can be 470 microwatt, C2 can be a 470 microwatt. Okay, these are one set of values. Okay, and and this is used when more current is needed from the circuit, definitely. So, and a power transistor is used, and since these two branches are coming like in parallel to each other, so the final current will be the summation of these two individual branches, and this is how the current adds up. Okay, and sorry, this is not NPN transistor, this is PNP transistor, because arrow is headed towards inside. So take note of this. This is PNP transistor, PNP, 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 not NPN. Okay, so that was a mistake that I told that it was NPN. No, this is PNP transistor, and accordingly R1 is chosen as smaller than R2. Okay, since this is a power transistor, so adequate heat sink should be provided, so that the heat generated at these power ICs could be passed to the environment or the air or the atmosphere, and they can be taken out from the circuit. And R2 is definitely the limiting, it is connected at the base, so it is limiting the current that is passing through the base, definitely. And if we need more current Okay, if we need even more current, then we can use more number of transistors, but they should be connected in parallel, because we know that the current adds up in parallel. So output current can be doubled by using two voltage regulator in parallel. Okay, definitely. And more transistors can be connected in parallel for a higher current requirement at the output side. Okay, so if you require more current than this, then you can use more number of transistors. Okay, and they are connected in parallel. Okay, so one idea could be to use more, number of ICs, and one idea could be used more number of transistors. Okay, okay, now look at this small example that says that uh, power supply having output resistance of 1.5 ohm. Okay, output resistance supply a full load current of 500 milliampere to a 5, this is actually 50 ohm, not 500, to a 50 ohm load. Okay, determine the percent voltage regulation of supply and no load output voltage. So we are given with the output resistance R 0, full load current 500 milliampere, and the load value is 50 ohm. Okay, so for full load output voltage, V full load can be calculated by simply V is equal to IR, where I, this is the load current and this is the load value. So V full load, the voltage across this full load is 25 voltage. Okay, and therefore VR, okay, VR can be calculated as R 0, output resistance, into I full load by V full load into 100%, that is voltage regulation. VR is given as 1.5. Okay, I full load is again given as 500 milliampere or 0.5 ampere, and V full load we had just calculated from here. Put up these values, you will get the voltage regulation as around 3%. Okay, so first portion is complete. Second is the no load output voltage. So V no load is given by this formula, that is R full load plus R 0 by R full load into V full load. Put up the values, you will get a value of 25.75 voltage. That is the voltage that appears at its output side when no load is connected, is around 25.75 voltage. Okay, look at here. When no load is connected, the output voltage is 25.75 voltage. Okay, when full load is connected, the output voltage is 25 voltage. Okay, so the output voltage is changing when we are connecting a load. When there is no load, when it's just simply open, the output voltage is 25.75 voltage. That it is more, it is high as compared to the condition when we connect a full load, when we connect a load at the output side. So this 25.75 voltage drops to 25 voltage. There is a drop of 0.75 voltage from this condition to this condition. Okay, and this is a practical scenario. Okay, so this is what happens when you connect a load. There is a tendency that the output voltage will decrease. Okay, and we had seen these two graphs. If you can remember, there was a graph for line regulation, and there was a curve for load regulation. Okay, so try to relate this example to those two curves. Okay. Okay, so I think this completes your section, your topic on regulation, IC voltage regulations. Okay.